Hello, my name is Rodrigo Obando, and I'm here to present, I would say, a guided tour of the elementary cellular automata and beyond. And this is about arranging the behavior of the rules in the elementary cellular automata and other bigger spaces in a meaningful way in terms of the behavior. All right, thank you for coming. I'm going to be talking about the elementary cellular automata, um, and I hope that that was, I should have actually put that in there. I'm assuming that everybody knows what ECA is. But I'm going to talk about this under a context of a paper that I published a couple of years ago, a different way of mapping the rules, taking what I call primitives and finding the dynamics of the rules and then laying those out on space. And I'm going to show that in, let me go here to the next. So that's the abstract. This is actually published it's going to be published in the conference so they can read that at your leisure. But essentially what happens is when we study the cellular automata and we are interested in the dynamic behavior of the rules, we find that there was, at least it was not visible, how the different behavior was related to the actual rule. Because the rule indicates local behavior, not global behavior, in any complex systems. Trying to draw some information about the global behavior, given that the local behavior is sort of difficult. You know, the fact that we know what happens at the local at the local part of the rule, that doesn't mean that I'm going to know what happens in the global. So the majority of times that we've actually laid out all the rules and the behaviors is just, for instance, for the elementary cellular automata, which there are 256 rules, it goes from 0 to 255. And when you see the evolution of those, going from one to another, it doesn't really tell you much. It just simply shows different evolutions, but they don't come together. You don't see any rhyme and reason why they are that way. So we normally assume that they are just randomly distributed. But when I looked at this, and this I've worked for some time with this, I realized that maybe we were looking at the rules in a little bit different way. For instance, back when Langton, I think it was back in the 80s, it started to say, well, we can compute the lambda of our rules by the number of ones that we have in the rule. And it was assuming that every single one that you have in the rule will be producing dynamic behavior. But in reality it's not, because some of those rules, some of those mappings are saying, okay, when you have your central cell equal to 1, and then your output is going to be 1, there is no change. So there is no dynamic behavior. So I looked at it differently and said, okay, let's partition this into primitives. And then we have the primitive 0, which means that whenever that is 0 and it's actually going to go to 1, that's dynamic. It's going to introduce change. And whenever the primitive 1 is that the central cell is 1 and is going to be 0, that's dynamic. That's going to introduce this. So now I look at all the rules in the elementary cellular automata, and 204 is, for instance, the identity. The identity is 0 change. That means whatever comes into the rule, it is just exactly what comes out. And 51 is completely the opposite, because 51 is the complement. So whatever I have as a 0, it goes to a 1. Whatever I have as a 1, it goes to a 0. So this way we go from completely inert, nothing changes, to completely changing, and we have everything in between. We have, in fact, 256. But what happens with this is that when we order this, then there was no way, to sort of order that. And this is what I battled with for some time ago, and I had issues with that. And I say, how do I order this? Because every time that I map this, it will always go to maybe a two-dimensional view, and it never satisfied what I was looking for. So what I did is I looked at those and I realized that perhaps they are not perfectly ordered, but they are partially ordered. And here's, I have the partially ordered primitives, and then there are actually 16 primitives per, 16 primitives, and every rule has 2 primitives. So this 16 by 16 gives the 256, and then I can order all of this in a lattice. And this lattice, as you can see, so it's a partial order, and then by showing it this way, I can then navigate from one to another. But I do that now for primitive 1, primitive 0, and primitive 1. That gives me 256, and then I order this way. So I created then a simple view of that so that I could display the 256. Unfortunately, it's very, very little. We cannot really see that. I wish I could just go over to the screen and show you that. But then, for instance, if I go back in here, I do have a tooltip that actually magnifies that and reevaluates. So that's 204, that's identity. And that actually has a single 1 as the input. Now if I go all the way over here, that is 51, which is complement. Now we have everything in between. You can see this. The interesting thing is, for instance, the Sierpinski rules, the ones that produce a Sierpinski triangle. I actually found them all, hanging out over here. They're all together. No other depiction of the whole rules are actually having all those together. I mean, they are all exactly the same for a single one. So they're all around here. So it means that this way of showing the rules is actually showing clusters or groups of rules that have similar behavior. Now there was something interesting when I saw this. I realized that if you do the complement will be these rules completely, where are they? I think they are around here. Like that one. That one is the complement of one of those rules. But now, what are the other ones? You had to go and find them. But if I flip that, and then I say, go ahead and flip how I'm ordering. Now I'm going to explain momentarily how this is ordered. Let me evaluate this. When I flip this, first of all, this group over here, they all had primitive 0. They were all the same. Now they are all the same with primitive 1. So I flipped it. Now all of this is the same primitive 1. And each one of those is a variation of primitive 2. So it happens that now I find the complement rules in the same place. The interesting thing is, and this is what is deceiving, that was deceiving to me, and I said, when I looked at a table with all the evolution for a single one, and I looked at that and said, that is not the one that I was looking for. I was looking for another just like this one, but it's not there. Why? So I realized that just the same way that I'm using the complements, that you also have to reverse your input. When you reverse your input, now they will behave the same way that the complements will behave with a single one. And I'm going to wait for a moment here. I wish I didn't have to compute so much. But if each one of the rules is being computed by, twice, one for the small one, the other for the big one, because it's a tooltip. So now I come back and you can see all the Sierpinski complement together, just like the other one right over here. So they're all here together in the same group. So this way of putting the rules together, it actually shows you that there is some sort of structure in the space that I can actually look at. So here, let me see, this is rule 30. And rule 86 should be around here. There you go. Is that 86? No, it's 85. There you go, 86. So if you explore this, and this is it's going to be available, published, so you can actually explore this, you realize that there are a lot of things that are, all sort of behaving similar. Well, I had to flip it again, sort of to show this. So one of the first things that I did, the other things that I did, the reason for the beyond in the title is because one of the problems that we have with the bigger spaces is if we want to explore the 4 billion rules, which will be the next step. We have 256 here. We can put them in here. Even with this, we realize that it's a lot of computation. So I don't even want to think about, and I don't think that anybody has really explored the 4 billion rules of the next, for the range 2. So with this way of ordering the rules, it happens, and I didn't put this in here, every rule is joined to another rule to the left and to the right. And the difference between them is 1 bit. So there is only 1 bit of difference in between them. So when we take those 2 rules, let's say this one, or this one over here to this one over here. If you take those 2 rules and you say, okay, let's take these 2 and now map these 2 rules to the next space. So they go from the 256 to the 4 billion rules. So they are still the same rules, but now I can have variations in between them. And in fact, it gives me 256 in total. So I can expand this. It's like using a magnifying glass and say, I want to go inside this to see what is, or how is it that, for instance, a particular rule over here changes to this other rule. And since I'm not showing the connection between the rules, so I have another little thing in here that actually allows me to do that. So I think it's 236. This one actually writes which are the neighboring, the immediate neighbors. So 236, for instance, connects to 110. Let me expand this a little bit. So this is your class 4. And 110, so it's connected to 236. So what happens between a single line over here that actually becomes 110? And that's what I have. The next slide is the one that shows that. Here I can then say I want to go from, and then this is 236 to 110. So this is now expanding from 236 to 110, so all the variations in between the two. And this actually gives me 256. Because for every bit of difference, there are a total of 4 bits of difference, so that's 8 bits difference. So that gives me 256. And as you can see, it starts right over here. This is the mapped rule to 36, but this is mapped to the bigger space that goes all the way to 110. And now see how interesting all this over here? Everywhere on this side is just like the first one. And suddenly they start changing. And we go, the depiction of this is from no activity to more activity, or more dynamics. So in here, I started looking at this and I said, oh, this is very interesting. Look at all the kinds of rules. Some of them are similar. And I'll look at that. If you recognize 110, that's 110 mapped to the bigger space. And then I discovered something like this. And I said, wait a minute. That looks like 110. But it looks like I didn't run it for enough steps. And I believe there is another place that is. So here. No, I think that was it. So I looked at that and I thought I had made a mistake. There you go. There you go. This one. So I thought I had made a mistake. If you see, it has the same kind of evolution, going down that I recognize from 110. You go look at 110 and say, hey, that's 110. But I'm running it for 1,000 steps right here. So if I look at that now at half of it, it shows this one. And so I was intrigued. That was immediately what happened with this. And then I went ahead and I said, okay, let me collect this. In fact, I went and did other explorations in other groups 256, and I found a total of 4. They do exactly the same. So I took those and I call them high definition evolution of Rule 110, single input. So these are the ones that I collected also that they were similar. But this one over here, this is 110 projected to the rule, to the radius 2. So these 4 over here, if you see those carefully, you'll see, for instance, this pixel over here is actually reproduced in exchange for a triangle, and with another 2 pixels over here. This one over here is created a bigger triangle, higher definition triangle. See the staircase over here? It's a lot finer in here. So all I had to do to be able to show that was to make it, oops, that's not what I meant. I want it to be, now it's running. No, don't do that. Yeah. I need to do it. I thought I had done it. Thank you. Okay, there we go. 100. So here we go. So they are identical, except that it is higher resolution. So if I go to, 5. So it has the same behavior, and I think if I go to radius 3, it will be exactly the same, but even finer detail. So just by looking at something like this, I sort of discovered this, and I haven't seen anything like this, which is the same behavior of 110, but at a higher resolution. My question is it that the 110 behavior is something ubiquitous in many other places, and we will find it at a higher resolution? I still don't know. Yes?
What do you mean by higher resolution?
I mean is if you see the 110, you see the jaggies, that are formed right in here. When you look at this, the yagi is less prominent. So if you look at it from far away, this looks more like a straight line than that one.
Isn't that one, didn't you want the other one for more number of steps?
Yes, but if I just double the number of steps, now I can impose one on top of another, and they have the same place where you have the same triangles, the same, all the way to however many I have. And I didn't have to do anything except to run it twice. And it's a different rule. So if I do 100, or 300, if you go, no, it's too much. If you go very close to that, they look the same, except when you look closer, it is like a higher resolution. Let me go into the next one because I already run out of time. The next one is, you see the same way? So they look coarser, you know, in computer graphics, we call that in this case, the 110 is the map of the other one. So I found those that have that general behavior, except that they are at a higher resolution. My triangles are better defined, etc. If I go to radius 3, I'm sure that I'm going to find the same kind of behavior, but in such a way that if I continue doing that, I will be able to see a fine line instead of just even seeing the staircase, and I'll be able to see that. It's true that I have to use more steps, but at the same time, it's doing exactly the same thing as Rule 110. So 110 is like a blurred version of this pattern, you know, all the way to the ECA, which is what I remember that Stephen said. ECA, you know, is the first, is the lowest level where we find something interesting like class 4. So that's one of the things that I found, and I just wanted to show something like that. I need to investigate and look at the form of the rules to see if I can identify why, you know, how is it that they are related, so that these other rules are actually reproducing this pattern. And I want to see if this is a general rule. For instance, if I look into Rule 30, will I find a higher definition of Rule 30 in the radius 2, and continue with this. The other thing is that this method, I can, and I don't have it, but I should be able to go from the radius 2 and say, take 2 of those that are also neighboring, and then open it up, go to radius 3, and see another 256. So starting with the ECA, I can go deeper into the general sets of rule spaces. And just as a side, I do have a visualization of this using the HoloLens. Unfortunately, it's not with Mathematica yet, because I'm working, you know, I'm participating in the beta Unity link, which actually is going on right now, with Charles Poo. We're trying to do that, a link between Unity, game engine, and Mathematica. But I do have a version of this in 3 dimensions, so I can walk around it and look at the different things in the space. Unfortunately, it's implemented in C#, and so it's not in Mathematica. I wish I had it, but if any of you are interested, I have the HoloLens, not here with me, but I have it around, have it in my room, and I would like to show you. And that's about it.
A couple minutes for questions.
All right. Drill.
I had one question.
Yes.
I'm wondering, how would you, I've just been reading the, like, I don't know if you, like.
No, I have not. I know that you mentioned that one.
Yeah, we talked about this. There's a paper that kind of discusses, like, it's all about formalization. It's a language of particle interactions. So I'm wondering if it can be used, they formalize language of situations, like, kind of just these repetitive, larger structural patterns.
Right.
Like gliders. I'm wondering if, are you going to formalize a lot of this? This all looks pretty qualitative, I guess.
Yes, yes, and that's the idea. You see, the first thing that I wanted to do was to organize this, to see like this one. I don't think I would have ever found something like that just by randomly going into the 4 billion rule space. So by looking at that, I want to see then how is it that the primitives are expressing the rules, you know, and then formalize it. But yes, yeah, I've been looking at all kinds of papers like that, and you know, some do it certain ways and some other ways, but they don't necessarily map the space like I've been trying to do.
Yeah, I mean, the paper here goes through flexible time, but they don't go through radius. They kind of
Just, I know, that's, I'm trying to go to radius 3, which is, 2 to the 128, so it's quite a bit.
So I was going to ask, if you have other methods of searching for these similarities.
I had a student, well, he graduated, and he was actually looking, a year ago I presented a probabilistic ECA, and he was doing something like that to find, but the way that we were doing it is finding it in the neighbors, and we found something like that, like you saw the Sierpinski, they're all together, so we could actually find them very quickly. But I'm thinking that what Stephen was showing yesterday could be used for something like that. When I saw it, I said, yes, because I could use it with images and then look for these kinds of patterns. All right?
You mentioned briefly at the end having C or C++ code for a 3D version.
C#.
What is it that evolves? You're dealing with CAs that are like tetrahedra evolved?
No, what I do have are cubes that have the images, the cellular automata output on top of it, and then I have it in 3 dimensions, ordered in this lattice, but I have the 3 dimensions instead of just having it flat, so it is easier for me to navigate and look around. Yeah.
If you have more questions,
All right. Thank you. Thank you. Appreciate it.